Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to continue our discussion on similar triangles, but we're going to look more into how do we find missing pieces, missing side lengths of diagrams where similar triangles are present. So we've already talked about, the shortcuts for proving triangles are similar. Now we're going to look at, okay, if we know triangles are similar, can we find the lengths of missing segments in those diagrams? We're going to skip the do now. We've already done examples of solving proportions, so we are going to skip those four, and we're just going to jump right into our theorems. The first one is called the triangle proportionality theorem. This can also be called the side splitter theorem. Right here. And this says if a line parallel to the side of a triangle intersects the other two sides, then it divides those two sides proportionally. Now, we've already talked about triangle mid-segments, where we have a triangle and we find the midpoints of two sides and draw a segment connecting those. We also know that the mid-segment will be parallel to the opposite side. So, in this triangle proportionality theorem, the difference is that mid-segment, right, can be anywhere on the triangle as long as it's parallel to the opposite side, right? So it could be up here, it could be down here, right? It doesn't have to go through the midpoints of the other sides. It just has to be parallel to the other side. And if it is parallel to the other side, then we're going to get this proportional relationship right here. So AE, the ratio of AE and EB is going to be equal to the ratio of AF and FC. Now, we could have already came up with a relationship. All right, we're going to take a little tangent here. But let's say well, you know what? I could just use the triangle we have there. That would make more sense, wouldn't it? So in this diagram, I already have two similar triangles, right? I've got the red and the blue. And we know those are similar by AA. And we could go through the proof, but right, they both share angle A, so that's one set of congruent angles. And then because these lines are parallel, we have corresponding angles that we could also say are congruent as well. So triangles are similar by AA. This would allow us to write a proportion. If we do AE from the red triangle and AB, because those are two corresponding sides, AE and AB, and then two other corresponding sides, AF and AC. So we could have already come up with this proportion that would work. And we're going to look at the proof below for how we can essentially go from this blue box to this pink box. So it's just a variation of what we already know. Again, this segment or this line that we draw through the triangle creates two similar triangles, and then we're able to get this proportional relationship out of it. So let's go look at the proof. Maybe it'll make a bit more sense what I'm talking about once we go through that. I may have to make this pretty small. Oh, there we go. All right, so we are given that EF is parallel to BC. Right, and that was just the hypothesis of our triangle proportionality theorem above. We want to prove that AE, the ratio of AE and EB is equal to the ratio of AF and FC. So I'd encourage you to pause the video. I do give you the statements, so read through the statements and think about what reasons could I use to justify those. And then once you've filled out as many as you can, come back here, join us for the discussion, and we'll piece the rest of it together. Okay, so this was given, right? EF parallel to BC. And then what I talked about up above, angle A congruent to angle A. That would be the reflexive property of congruence. And I am just going to sketch these two triangles out again. Do red and blue. So they both share this angle up here at A. And then angle AEF congruent to angle B. I'll just mark those. It's the same one I marked up above. And this would be the corresponding angles postulate. Again, because we know those lines are parallel, so corresponding angles are congruent. And then triangle AEF is similar to triangle ABC. That would be by AA similarity. That would be the shortcut we could use. Okay, so once we prove those two triangles are similar, we now have this proportional relationship. AE, the ratio of AE and AB, one from the red, one from the blue, is proportional to the ratio AF and AC. So these two are red sides, and then we have blue sides. And right here, this would just be definition of similar, definition of similar triangles. So if the triangles are similar, well, all of the corresponding sides will have the same ratio. And they could have added in this third ratio. We're just not going to need it in the proof, right? But they could have added in both of those ratios also must be equal to EF over BC. Again, that would be the third ratio. It's just not needed in the rest of the proof, so we leave it off. All right, moving on to the next one. We have AB is equal to AE plus EB, and then we have AC is equal to AF plus FC. Well, basically they're just saying, right, that entire segment AB is made up of the two smaller segments AE and EB. And this is just the segment addition postulate. And they're using it for both sides of the blue triangle, right? So this entire side and this entire side. Next, I guess we need let me put a line break in here. There we go. So then they say that the ratio of AE over AE plus EB is equal to the ratio of AF over AF plus FC. And here we have some substitution going on. So if I look at both of these statements right here, right? If I know that AB is equal to this, well, I can make that substitution here, and I can make that substitution there. So substitution property of equality. Then there's an algebraic property going on. So it looks like they cross-multiplied in the next step. Multiplication property of equality. And then they just distributed on both sides, right? They distributed AE to both AF and FC, and then AF on the other side. So just distributive property. And then how do they go from this line to the next? Looks like they subtracted something. Well, what did they subtract? Notice that we have an AE times AF on both sides, so they could subtract that product from both sides. So subtraction property of equality. And then finally, it looks like they divided both sides by a certain product. Let me show you. It may not be obvious right away what they divided both sides by, but let me show you here. So they have AE times FC is equal to AF, AF times EB. And then if we look at the next line, we have an EB in our left denominator and an FC in our right. So we're definitely dividing this side by EB and this side by FC, but we're actually dividing both sides by both of those. All right, and you'll see what happens. These simplify, and we are left with what we have below. So AE over EB, whoops, is equal to AF over FC. So it is division property of equality. They're just dividing by a product, not just a single quantity or a single entity. I don't know why I wrote the whole thing out instead of POE, but that's okay. And there's our proof. So again, like I said above, this is not, a completely new proportional relationship. We could have already come up with this. Let me erase some of this stuff. We already knew how to come up with this, right? Corresponding sides of similar triangles have the same ratio. This is just a little bit of an offshoot of that. Doing some algebraic manipulation allows us to arrive at this. So it's going to be up to you. When you see a diagram like this, choose whichever proportion is going to be easier to solve, right? Maybe it will be easier to use the entire side of the blue triangle, right, for both. Or maybe it'll be easier just to use this part. So again, it just gives you more options when you're solving similar triangle diagrams. Okay, let's move on, and we'll eventually get to some actual diagram problems. First, though, we're just going to look at the converse. If a line divides two sides of a triangle proportionally, then it is parallel to this third side. Again, this is just the reverse of what we set up above. So if that proportional relationship is present right here, then that implies that these two lines or segments are going to be parallel. Okay, let's just do question 1. Should be pretty quick. You are going to use the triangle proportionality theorem here. And notice there'll actually be several different ways you could set this, or a couple different ways you could set this up. So go ahead, pause the video, see if you can figure out the length of CY. Well, I'm going to let this length of CY be equal to X. Let me label it as such. So based on the triangle proportionality theorem, I could set up the proportion 10 over X is equal to 9 over 4. Pretty easy cross multiplication here. So that's going to give me 9x is equal to 40, which means x is 40/9. And you wouldn't want to give me a decimal because that decimal is not a terminating decimal. Now, before you learn the triangle proportionality theorem, you still could have solved this problem. It just would have required a different setup, right? You would have instead had to do 10 over 10 plus x is equal to 9 over 9 plus 4. Still could have solved it fairly easily using cross multiplication. It just would have been a couple more steps because your denominators are sums rather than just single numbers or variables, but still possible. And then, again, if you go through and solve the one in red, you will still get 40/9. All right, moving on to our next theorem. This is called the two transversal proportionality corollary. So if 3 or more parallel lines intersect two transversals, then they divide the transversals proportionally. So if we look at our diagram, A, B, C, D, and E, F are all parallel, and then we have this proportional relationship. AC over CE is equal to BD over DF. And I could keep adding parallel lines in here, and this ratio works just the same. So let me we're not going to do the problem on this paper. Let me give you a slightly easier example. We'll save that problem for class. But let's say I have some transversals, and let me throw some parallel lines in here. And you'll notice the parallel lines do not have to be spaced out. Whoops. The parallel lines do not have to be spaced out the same, right? I could put this in real close, and this relationship is still going to hold. Let me label some stuff here. Let's say that's actually 2x. Over here we have 10. We'll have 5, and we'll have, well, it can't be 5 either. Well, yes, it can. We'll make this 8. So pause the video, see if you can set up a proportion here that you can solve to figure out the value of x. Okay, so based off of the theorem, we would have 2x over 8 is equal to 10 over 5. And then again, we would just cross multiply to solve. That would give me 10x is equal to 80. That would give me x is equal to 8. And we do have one more theorem to hit today before we shut down this video. It's unfortunate we don't have time to go through all the proofs for these theorems because they are interesting, but then our video would be pushing an hour or more. The last theorem we're going to look at is the triangle angle bisector theorem. And this theorem says an angle bisector of a triangle divides the opposite side into two segments whose lengths are proportional to the lengths of the other two sides. So if we have an angle bisector, which means that it's a segment that splits two angles into ones that have equal measurements or ones that are congruent, so those angles up here. We don't need those because there's already arcs. I was just showing you which ones we're talking about. If that's true, then we have this proportional relationship right here. So the ratio of BD to DC is equal to the ratio of AB to AC. Now, it is important, these two triangles in this diagram, I mean, I guess there's three, but the two, not looking at the large one, so these two triangles right here, these two triangles are not actually similar. They only share one angle, one set of angles that are congruent. So they still have this proportional relationship, but these two triangles themselves are not similar. And if we'll probably do the proof one day in class, the proof, when we sketch some auxiliary lines, you end up seeing some similar triangles going on, and that's where this proportion comes from. But we would have to add some extra segments and create some other triangles to see the similar ones. So it's not the pink and blue ones we see in the diagram. I just want to point that out, that those two triangles themselves are not similar to one another. That being said, we still see this proportional relationship. And again, we are going to apply this down below. I do want to show you that this can be written in a couple of different ways, right? So let's say I cross multiply here, and I get BD times AC is equal to AB times DC. And let's say I divide by, I'm going to divide by AB times AC from both sides. Well, these would simplify. So I get BD over AB is equal to DC over AC. So again, these two right here are algebraically equal, right? They're just written in different ways. So when you take a look at the diagram, maybe you're thinking, well, could I set it up this way? You could, as long as you could justify why the way you're setting it up is really equal to this conclusion right here. And again, through algebraic manipulation, sometimes you can set up the proportion multiple ways. Let's go ahead and apply this to one problem down below. Let's apply it to number 1, pause the video, solve for x, and then we will have one final discussion before we're done. Okay, so I'm just going to set this up the way we have in our original conclusion here. I don't know what kind of star I just drew. That was not very good. There we go. So I'm taking the ratio of the side that's being intersected by the angle bisector. So x plus 2 over 2x plus 1. Now in my other ratio, I have to start with the side that's part of the x plus 2 triangle. So 10. 10 has to go in my numerator. This would not work if I did 14 over 10. Right? I could switch these as long as I switch these, but I couldn't just switch one of them. Otherwise, our proportion would not be the same. So a little cross multiplying. This gives me 14x plus 28. Cross multiply with the other two. I get 20x plus 10. Don't let me forget my x. Subtract 14x from both sides. It's going to give me 28 is equal to 6x plus 10. Subtract 10 from both sides. It's going to give me 18 is equal to 6x. Divide both sides by 6, and I get x is equal to 3. And we are done. All right, I think that's enough for this video. Feel free to work on the other problems, but we will have some time to practice those in class as well. As always, enjoy the rest of your day, and I look forward to seeing you next time.